Okay, so we're very happy to have here Oehad Shamir. Oehad Shamir has studied in Jerusalem with Tali Tishby. Then he spent some time in wonderful New England in Microsoft Research. Since then, he's been at the Weizmann Institute, and although he's a pretty general researcher, he's already a world-leading famous researcher in his area. So without further ado.
Okay, thanks for the introduction and for inviting me. So this talk is based on a bunch of papers, most of them together with my two students, Itai Safran, who is graduating this year, and Gilad Yehudai. And feel free to stop me at any time if you don't understand something or want to ask a question. So let me start by a question. How many people here didn't hear about deep learning or neural networks? Okay, great. So I can keep the motivation part pretty brief. Okay, everybody motivated? So let's continue. Okay, so in this talk, I'm going to focus on plain vanilla feed-forward neural networks that can be modeled as neurons, where each neuron computes some simple function of this form, so some linear transformation composed with some fixed nonlinear function. For example, the ReLU function is popular nowadays. And we put these neurons in layers and stack them one on top of the other. So overall, the function that these neural networks compute can be mathematically expressed like this. So if it's a depth k network, we do k operations of the form x maps to some linear function composed with some x nonlinear function, where all of these W matrices and B vectors are the parameters of the network. And when we train neural networks, what we basically do is to take some data and try to minimize the expectation of some loss function, which measures how well we do the predictions in expectation over the data, with respect to the parameters of the network, which here I'm denoting as theta. And the big theoretical problem here is that as an optimization problem, this is a very, very non-convex problem. We know that in the worst case, non-convex functions cannot be optimized, no, at least in general. On the other hand, we are able to solve these optimization problems and train neural networks successfully. And in fact, with very, very simple local search methods. So things like gradient descent or stochastic gradient descent, where we pick some parameter vector and do a small step in the direction opposite to the gradient, or at least in expectation. So maybe you have some zero mean noise here. But this is basically just some local search procedure. And somehow, even though the landscape looks like this, we always manage to reach the C. The big question is, why is that the case? This question is very and surprisingly difficult. So I'm going to start by giving you a few examples just to show how difficult this problem is already for very, very simple networks. So here is one setting that a lot of people looked at. So suppose we wish to train maybe the simplest possible network that you can think of with a ReLU activation. So this is a function which has this form with parameter vectors wi. And suppose I want to train this network on a data that is perfectly labeled by a network of this form. And the inputs, the x's, are, say, just from a standard Gaussian distribution. So writing it as an optimization problem, we're basically trying to optimize a function which looks like this, again, over the parameter vectors w. So for any given x, this is the output of my network. And I want to make it as close as possible to the prediction of the target network, which I'm going to assume has this form. So every parameter vector is just a standard basis vector, and they're all orthogonal to each other. And I want to show that at least for a simple network, gradient descent works. And moreover, because this is such a simple network and everything is Gaussian, I can even write it down in closed form without expectations. So it's some kind of a linear combination of functions of this form. It involves the angles between the vectors and norms. And we may ask, what is provably the performance of gradient descent if I run it on this thing? And the answer is that no one knows as long as the number of neurons is larger than 1. And again, despite much work in this direction. So we might ask even like more basic geometrical questions about this functions. For example, does it even have spurious local minima? So local minima that are not global, so that if I use a local search procedure, I might get stuck in them. If the function doesn't have local minima, then it's a very good indication that gradient descent does work. And even that basic question is surprisingly difficult, because how do we prove that a function has bad local minima? We need to take a derivative, equate to 0, figure out where are the stationary points, and then for those stationary points, see if one of them might be a local minima. So that's the standard approach, but unfortunately, it doesn't work here, because no one has any idea how to compute the roots of this equation for this function. As far as we know, there might not even be a closed form expression for the roots, and when we don't have a closed form expression, it's very difficult to prove anything. Nevertheless, it is possible to show something here. So recently, in joint work with Itai, we were able to show that, unfortunately, and despite what many people in the community hoped, even this simple problem has a bad local minima, at least for some values of n, number of neurons, which is sufficiently large. And even that we weren't able to show really explicitly. It was actually using computer-assisted proofs. So roughly speaking, the idea was that we ran gradient descent for a long time on this function until we found a point which is almost stationary, where the gradient is very, very close to 0. And then we use some a rigorous certificate that we developed that tells us that if the gradient norm is small enough and the Hessian at that point, the second derivative, is sufficiently positive definite, then we are provably very close to a local minimum. So we developed it. We use it to show that for many values of n, there are spurious local minima. But one handicap of this approach is, A, it doesn't give us much insight about the structure of these local minima. And second, it only works for particular values of n, because for any n, I need to run gradient descent. So in particular, it's still open whether this problem has a spurious minima for any large enough n. Yes? Yes, so I mean, so I have, so this would be a bad local minima. So it's a local minima, but it's not global. And in the context of this problem here, we know that there is a global minimum with a value of 0, in particular if you pick each wi to be ei. So the question is, are there local minima that have a value larger than 0? Yes?
And the same thing would happen if you replace this value with some other function, which I say smoother, but it sort of approximates the value or something like this.
So the question...
Then you can actually differentiate those things.
Yeah, so first of all, because this is a Gaussian distribution, even though the ReLU is not differentiable at a point, this function is still differentiable everywhere except at the origin. So that's not so much of an issue. Regarding other activation functions, in general, we don't know. There were some specific cases, like if you replace it with a quadratic function, that we can show things, but nothing in general, even if you...
In a quadratic case, it's also as difficult as you say?
So actually, in the quadratic case, I think it might be possible to show that there are no spurious local minima, but I'm not 100% sure. But the kind of networks that are used in practice usually use something like this, a monotonic function. So, yeah. Yeah. Mm-hmm. Yes. Yeah, the point is that with this certificate, I know that gradient descent reached a point very, very close to a local minimum. And this function is also locally Lipschitz. So if at the point I reach with gradient descent, the value is 1, and I know there is a local minimum at a distance of 0.0001, then I can prove that this local minima cannot be global. Yeah. This is all things I can do with the computer in a rigorous manner, so yeah. OK. Let me give you now an example in different context that people looked at, which is linear networks. So that's standard networks where I removed all the nonlinear activation functions. And what I'm up with is just a linear function parameterized in a weird way. So I basically get x maps to x times a product of matrices. So again, this is just a different way to write a linear function. And for these kinds of networks, no one really uses them in practice, but the idea is that it's widely conjectured that optimizing these networks has all kinds of characteristics in common with optimizing nonlinear networks. So, at least if we want to say something about nonlinear networks, at least we should be able to say something for linear networks. And indeed, we can say more here. So in fact, we can prove that there are no spurious local minima under very mild conditions. So now the natural question is, does gradient descent actually work here? And you might think so, because there are no bad local minima. So what possibly might go wrong? So let's look at a very, very, very special case. Suppose that these networks, the matrices are 1 by 1. So it's one-dimensional networks, just scalars multiplied by a product of numbers, which are my parameters. And suppose I want to train this network to work well just on a single data point. I want that given the input 1, the network will output -1. OK, so I can write it down as a function of this form. There should be a square here. OK, so basically, I want this product to equal -1. And suppose I look at plain vanilla gradient descent with random initialization, which is maybe the simplest method. People actually use these things in practice. So here we can prove something, but maybe not what we would hope for. So gradient descent does converge here, provably. And provably, it'll take it exponentially many iterations in the depth of the network. So this is both in theory and in practice. When you actually run it on a depth larger than 7, it basically never converges. So this is for 1 by 1 matrices, but empirically, this thing also happens sometimes in larger networks where the matrices have higher dimensions. Something positive for linear neural networks, we already have a problem with this very simple case. Let me give you like a brief explanation of the proof ideas. So the difficulty here is not bad local minima, but something else, which is what is known as saddle points. So the point is that if you look at this function, and any point such that wi is 0 for many, many entries, this would be a saddle point, so something which looks like this. It's not a local minima, but if you get here, things are very, very flat, and it'll take you a very long time to escape and further decrease the function value. And it's a high order in the sense that the gradient here is close to 0, the Hessian is close to 0, also higher order derivatives, depending on how many w's are equal 0. So a little bit more specifically, OK, so we might hope that, OK, there is these bad saddle points, but maybe gradient descent evades them. And unfortunately, it really doesn't. So if we look at some kind of standard initialization strategies, one approach is to initialize every wi independently from a zero mean distribution. The problem is that of IID random variables is not very well behaved. For just about any distribution you'll pick, either the product with high probability will explode with the number of random variables, or will implode to 0, and in 0 we have a high order saddle point, so we're kind of stuck. People look at other initialization strategies, which also work here. So for people looked in the context of linear networks at initializing each matrix close to identity. So here it would be initializing close to 1. But again, you get this problem of you're getting stuck at a saddle point for a very, very long time. Because basically, if you start with all the wi's close to 1, gradient descent decreases all of these wi's. But that means their product goes exponentially fast to 0. So you're next to a saddle point, and you get stuck, which eventually you manage to escape the saddle point, but it'll take you an exponentially large time. Any questions about this? OK. So clearly, if we want to show something positive here, we need to make more assumptions to circumvent these difficulties already for very simple cases. And this is like the focus of a lot of recent work in the community. And people have come up with various assumptions. Some of them are known to work. For example, if you assume your data can be separated by a linear function, or you want just guarantees with respect to linear predictors, or you look at very, very, very specific learning problems, like learning XOR in 2 dimensions or stuff like that. The problem is that it's hard to scale. It's all kind of specific. And if you want guarantees for large-scale neural networks and realistic problems, it's kind of difficult. So one approach that is increasingly popular to tackle that, and that I'll focus more on in the rest of the talk, is to consider actually networks which are very, very large, also known as over-parameterized networks. Roughly speaking, that means that I take a network that is much, much bigger than what I need to solve the problem, like ignoring computational constraints. So this might seem a little bit weird. I mean, why making the network larger and more complex might make the problem easier? So a possible intuition for this, if you think of this problem as an optimization problem, is that by making the network larger, I have more parameters. And that means that my optimization problem lives in a higher dimensional space. And in very high dimensional space, it's kind of harder to get stuck somewhere because I have so many possible directions which I can try to further decrease my function, that maybe it's rarer to have the situation, you know, like a local minimum, which is really local. It's really a minimum in all possible directions. At least the intuition. And also, from more practical viewpoint, this is a reasonable assumption because neural networks used in practice are really very large. So large that, like, we know that in you can basically train them to output any kind of output that you want. There have been all kinds of works on that. But anyway, it's a reasonable assumption. So let me give you a more empirical example of how over-parameterization helps. So this is from a paper of mine from 2014, which is ancient prehistory in the context of deep learning literature, but I think it's illustrative. So what we did was we took some data and that we actually generated using some depth to width 60 ReLU neural network. We created the data, we threw away the network, and then we simply tried to train on this data with a network which was x times wider, also depth 2, but with neurons by some factor x between 1 and 8. So it turns out that if you try to train with a network with the exact same architecture as the one generating the data, so this is the blue line here. So this is like the mean square error as a function of the number of iterations. Mean square error just on the data. So it doesn't work too well. Like, it decreases to something, but definitely not to 0, even though that we know that it's possible to get 0 error on this data, because we generated with the network. However, if you increase the size of the network times 2, times 4, the error rapidly decreases, and by a factor of 8, you basically get 0 error very, very quickly. Okay? So this is also, this benefit of over-parameterization is also something that you can see empirically. So both this experiment and many other experiments that people did. Okay, now let's go back to the two examples I mentioned earlier and try to look at them again through this lens of overparameterization. So we talked about this case where we want to minimize networks which have this form. And suppose we talk about overparameterization in the sense that I now allow the number of neurons in the network that I train to be larger than the number of neurons in the target network, the network really creating the label of my data. So what I'm going to show you here is if you just do gradient descent with random initialization, and you do it many, many times, what percentage of the runs convert to a bad local minima? So first, let's look at the case where n equals k. So the size of the networks is the same. And there it turns out that as the network size increases, being stuck at the local minima is actually pretty common. So by size 20, you get stuck 94% of the time. But now, let's suppose that I make n slightly larger than k. In particular, suppose I just add one neuron. So now n would be k plus 1. And the numbers already become very, very different. So whereas here, when n equals k at 19, I got stuck 93% of the time, just by adding one neuron, I'm now getting stuck only half of the time. And in two neurons, if n is at least k plus 2, we were actually never able to find any bad local minima, at least with a gradient descent.
Do you have a guess what this theory is about?
People have various conjectures that maybe it's like k log k or something like that, but no one knows how to prove it. So this is just, so probably if you take n large enough, k plus 2 also won't be enough, but log k, I would bet that it is. Okay, so I have no theory here, but empirically this is very, very clear that overparameterization helps. If we go back to the example of linear networks, I told you earlier that when I look at linear networks where every matrix is a 1-by-1 matrix, gradient descent provably takes exponential time to converge. However, following our paper, there was a very nice result by Du and Hu that showed that if these matrices are large enough, in particular if the inner dimensions are at least the depth times the input dimension times the output dimension, instead of taking actually many iterations to converge, it takes only logarithmic in the number of iterations to converge. So just by polynomially increasing the width of the network, we get this double exponential improvement, provably, in the performance of gradient descent. Okay? Okay. But these are linear networks. In practice, no one really runs the linear networks. What about nonlinear ones? So in this front as well, there have been a lot of activity, especially in the past year or two, which managed to provide positive results for nonlinear networks using overparameterization. So even if these are complex networks, we can nowadays show that they are successfully trained or learned by gradient-based methods, assuming the network is large enough. And there are various variants of this, but these are all, at least in my view, kind of based more or less on the same fundamental idea, which I'm going to talk about in the next slide. And I want to emphasize that currently this is pretty much the only general technique that we have for analyzing nonlinear networks on nonlinear problems. So to give an intuition, let's start by considering just depth to networks. So these are networks I can, and without a bias. So I'm going to write them in this form. So the wi vectors and the ui weights are my parameters. And suppose I'm trying to train these networks with gradient descent. Now, the way that these networks are usually initialized by kind of variance considerations is such that each individual weight ui in the output layer scales down with r, with the number of neurons. Something like 1 over square root of r. This is basically to ensure that in my randomly initialized point, the outputs are not too big, and That's really the kind of heuristics that are used in practice. So what happens if ui scales down with r, and now I make r very, very large? So notice that the gradient of this thing with respect to wi scales with the magnitude of ui. And that means that for large enough r, at least initially, the gradient steps almost won't change wi, because the magnitude of the change is proportional to the magnitude of the gradient. The gradient scales down with r, because it scales with ui. So r large enough, we're almost not going to move, at least initially. And what we can conclude from this is that if I use enough overparameterization, r is large enough, and I look at a regime where I don't do too many iterations, depending on r, then the dynamics of gradient descent or stochastic gradient descent is almost the same as if we just fixed the wi vectors at their initial random initialization and just trained the output layer, just trained the ui weights. Okay? And these positive results are basically based on this insight. Okay, but let's take this thing, make this explicit. Suppose that's what I actually do. I fix the wi's at the random initialization and train just on the ui's. So that actually leads us to a very well-known and old technique in machine learning, which is known as learning with random features. So what's learning with random features? So the idea is that you have some set of nonlinear functions, which in the previous slide was the set of ReLU neurons, but could be many other things. And I just pick some of these nonlinear functions at random, and we learn a weighted combination of them. Okay, so this is just learning a linear predictor over some nonlinear mapping that we chose randomly and then we fixed. It is not affected, this mapping is not affected by the training dynamics. And most of the recent positive results can be cast in this kind of random feature framework. So you can replace the depth 2 by higher depths, and then like instead of ReLU neurons, you have more complicated neurons that you eventually learn a linear combination on. But again, the dynamics are such that you can think of these subnetworks as being fixed in the random initialization. People also analyze these things through kernel methods, and I'm not going to go into the details, but I can say that in general, if you use any kind of kernel predictor, which is an important class of predictors in machine learning, so any kind of kernel has this form. So given x, it's a weighted combination of a kernel function on the input x and xi, where xi are like the instances in your training data. So in a statistical learning setting, where my training data is sampled for some distribution, this is exactly a random feature. xi is some random variable that I pick at random, and then I just learn a linear combination over these kernel functions. Now, random features is, as I said, it's a very well-known technique in machine learning. It kind of combines the ability to learn a nonlinear function because of these nonlinear mappings with the simplicity of training a linear predictor. Because once I fix the FIs and I just train the UIs, this is a linear prediction problem. It's convex in general, and we can do it very efficiently. I mean, in fact, this method goes way back to even like one of the very first machine learning systems. So I guess many of you maybe took a machine learning course, learned about the Perceptron algorithm. So that algorithm was originally developed to train this machine, which was the Perceptron machine assembled at Cornell in the late 1950s. And that machine was actually a linear predictor over random features. So there was like one layer of random connections from the input with a threshold to a bunch of neurons. And then using a Perceptron algorithm, people learned a linear prediction over that. So this is kind of a technique that is important and interesting in itself. And by the way, in the pictures here, you can see all of these random connections, which were, of course, physical wires that were painstakingly assembled by hand. Anyway, so why are random features good? So besides this thing of using linear learning to train nonlinear predictors, it also has a very good condition of universality. So under mild conditions, the point is that if you take sufficiently many random features from reasonable classes, in particular ReLU neurons, then you can basically approximate and express any kind of continuous function you want on a compact domain. So kind of the idea is that for suitable function classes, this is kind of a result from approximation theory, you take any kind of target function g, then there exists some bounded function alpha so that you can express this g as the expectation over the random features of the feature times alpha. And once you have this, you can use basically concentration of measure arguments to say, if this holds an expectation, and I now just sample sufficiently many random features from this distribution, then I can find coefficients so that this average would approximate the target function. So basically, if I take all of this together, it means that using a sufficiently overparameterized neural networks, I can learn as well as random features. And with enough random features, I can learn basically anything I want. So it could be polynomials or other small networks. For every such function, I can figure out some kind of bound on how many random features or neurons I need. And if I have enough, I'm going to be OK. Yeah?
So more overparameterization means more random features?
Yes. Yes. So you make the network wider. Yeah.
So all this presentation discusses the training error. You claim nothing about the generalization.
So actually, the nice thing about this is that it works both for training error and for generalization error. OK, the technical details are a little bit different, but this kind of thing can hold on some finite set of data points, or it can be an expectation over some distribution. You can make it work both ways. Any other questions? Yeah.
Is there a point where there is a trade-off? I mean, how much overparameterization?
That's going to be the rest of the talk. There's a catch here. OK. So so are we done? Did we manage to prove that we can learn anything and go home? So unfortunately, it's not that simple, because this is the way that I presented these things to you. It sounds a little bit like free lunch. No matter what you want to learn, you'll be able to learn it. But when you take any kind of introduction to machine learning course, you generally learn that in machine learning there are no free lunches, that we actually have rigorous no free lunch theorems that imply that you can't really learn any function, even if you ignore computational considerations, just from statistical considerations. So we can't really learn any function. And when we choose any kind of class of predictors, it could be random features or linear predictors or decision tree or whatever, it always induces some kind of inductive bias, some kind of assumptions that we implicitly make on what kind of input-output relationship we can express. So one can ask, what is the inductive bias of random features in this kind of generality that I presented things so far? Take a kind of random feature model. What is the inductive bias? And also, because we're interested here in the context of neural networks, what is the inductive bias that we want for neural networks? So what would be like a reasonable thing? So if we train neural networks, then we might hope to be able to learn target functions that we can actually induce by a neural network. Because if our learning problem, there is no neural network that expresses the prediction function I want, then we might use something else in the first place and not neural networks. So it's reasonable that we can learn target functions induced by simple networks. And let's take the simplest, really simplest possible case. that I want to learn a target function that I can express just as a single ReLU neuron. Okay, X map to W transpose X plus B. And this is an easy case because we know that we can train single ReLU neurons. So people actually rigorously prove that when you have a single neuron and you train it with the squared loss and expectation, say, over Gaussian distribution, you can actually train these things efficiently with gradient descent or stochastic gradient descent. Okay, so we know it's an easy problem, but now we want to understand whether the random feature as a scientific theory for explaining deep learning, can it explain this positive learnability result, that we can actually learn single ReLU networks. Okay? And unfortunately, and this is in a paper together with my student Gilad that will appear this NeurIPS, we unfortunately showed that this is not the case in a very strong sense. So this is like one of our main theorems. So suppose that we use a random feature model to try and learn a single ReLU neuron. So take f to be any family of functions you want, as long as the magnitude is kind of much less than exponential in the dimension. That's a very reasonable assumption. And take any kind of distribution over tuples of R random features for any R which is less than exponential in the dimension. Then what I basically claim is that you won't be able to learn a single ReLU neuron, in the sense that I can always find, for any function class in any distribution you want, some ReLU neuron with weights which are polynomially bounded, such that with high probability, if you take the random features that you got and try to fit any kind of linear predictor on top of them, try to find some linear combination of these random features that will even approximate the target neuron to less than some absolute constant, basically you won't be able to do it, at least with weights that are less than exponential in the dimension. And because networks with exponentially many neurons or exponentially large weights cannot be trained efficiently in general, with gradient descent at least, then you can't really do it. Okay, is the idea of the theorem clear?
What's the measure of those nasty neurons?
Standard Gaussian distribution.
I mean, how many of them are you expecting to...
Okay, so as stated, this is a worst case result. So I can only show there exists some neuron. If you assume a little bit more about the random features, you can show that this holds for any ReLU neuron where the norm of V is something, d squared or something like that. Yeah, which is what I said. Okay, so again, this thing implies that you can't use any random feature scheme. And again, I made basically 0 assumptions on what are these random features. Could be ReLU neurons, networks, kernel predictors, whatnot. So, and you can't even approximate a single ReLU neuron. So this is not even a hardness of learning result. This is just about approximation. If I tell you the distribution, you know everything exactly. You just try to fit this function. You can't do it. Which, again, I would argue that that means that, at least as a scientific theory, random features can't explain learnability, even of single neurons. And I'll explain later on the proof intuition, but maybe like very roughly, I would argue the intuition is that random features can't really work because they completely neglect the representation learning aspect of deep learning. So one of the things that apparently make deep learning so powerful is that it learns not just like the output neuron, but also the internal representation of the data inside the network that the higher layers use. And this is something that essentially requires you to change all the weights in the network. And a method that just fixes almost all of the weights in random initialization and just train the top layer, in some sense, doesn't capture that. Now, I should say this does not contradict mathematically the positive results I talked about earlier. The point is that when you look carefully at these results, you know that they all contain either implicitly or explicitly some kind of exponential dependency on the norm of the target parameter vector v, if we're talking about ReLU neurons. So if you take it polynomially large, like we do in our theorem, it's exponential. And also, it does not contradict the fact that random features is often a pretty decent, like, first method to try in practice. But it tends to work well in relatively simple problems. So for those of you who know learning data sets, so things like MNIST, recognizing handwritten images or variants of this. But if you actually try random features on a really state-of-the-art problems such as CFAR or object recognition in real-world images, it doesn't really work so well. And making an analogy, maybe these problems you can kind of learn with constant norm ReLU neurons, but to solve like the state-of-the-art things, you need higher norms, and then it doesn't work well. Just to briefly describe the proof ideas, so just to give the intuition, let me start by talking about a simpler problem of linear functions. So suppose I want to learn a single linear predictor, x maps to v transpose x, using a linear predictor. So this kind of function. And this we know is a very easy thing to do with gradient-based methods because it's a convex problem. But now let's suppose I don't know that, and I try to use the random features approach to explain why we can learn linear predictors. So it's a predictor, everything is linear, so it makes sense to use linear features. So my features are going to be wi transpose x, where wi I'm going to sample from the unit ball. And I want, with our random features, to be able to get low expected loss here. I want this to be small. Because everything is Gaussian, I can also write it equivalently as this, just the squared norm of the linear combination of wi minus v. So let me ask you, for this kind of problem, how large does R need to be if these wi's are just picked uniformly at random so that it would be small? Yeah, so it's just going to be the dimension. Why? Because as long as I don't have about d vectors, if I have, say, d over 2 vectors, then no matter what linear combination I take, it lives in some d over 2 dimensional subspace. And probably this subspace is not perfectly aligned with v. V has some significant component outside this subspace. So no matter how I pick the ui's, I won't be able to make this small. OK, so this is just a linear prediction problem, and d might not sound too large. But it already shows a gap here between what we know is the true answer and what the random feature approach tells you. So we know the true answer is that you can learn linear predictors without any overparameterization. You can do it with r equal 1 if you allow yourself to play with the w. But if you do it with random features, you necessarily need something which scales linearly in the dimension. So already here, there is a certain gap. And roughly speaking, our proof idea is to show that the exact same thing happens, not for linear predictions in RD, but kind of in a function space, which is very high dimensional, where we show that the effective dimension of any kind of random feature that you take has to be exponential in D. So if the effective dimension is exponential in D, using kind of the intuition from the linear case, you would need exponentially many random features. OK, so a bit more precisely, what we essentially show is that the effective dimension of this function class of all ReLU neurons with polynomially large weights is exponential in D. OK, so take any space which is less than exponential in the dimension, you won't be able to capture this class, this set effectively. And just a little bit more in detail, the actual proof goes through some reduction. So first we show that random features can't really express a function of this form, x maps to psi of v transpose x, where psi is any kind of periodic function that you want, say some zigzag function. So the effective dimension of this class is exponential in D. And this is based on some ideas. For those of you who know about statistical query lower bounds, there are all kinds of close connections. If you're interested, you can ask me more about it offline. And then, once we know that it's impossible to learn these features, or to even express, it's impossible to even express these or approximate these functions, we notice that these are functions that you can approximate with a linear combination of ReLU neurons. Because a ReLU is basically one nonlinearity. And if I take a bunch of ReLU neurons and shift them, I can express any kind of piecewise linear function that I want. In particular, something that looks like a zigzag, which satisfies the conditions here. So if I was able to approximate ReLU neurons, I would have been also able to approximate these functions. But I can't. Hence, by contradiction, there must be some ReLU neuron that I cannot approximate well. It's short for statistical queries. So this is a certain model in machine learning that people have studied. And OK, I won't have time to go into the details, but it's based on all kinds of ideas from there. Any questions about the proof idea? OK. This is it. So I talked about this question, this big question of why can we successfully train neural networks. Nowadays, we know that overparameterization is probably a key piece. It really, really helps in practice. It also seems to help in theory, at least in certain cases. And moreover, there is also empirical evidence that this kind of idea that highly overparameterized networks don't change their weights too much is true to some extent. So, for example, there was a nice paper by Zhang, Benju, and Singer not too long ago that shows that on actual networks, really some parts don't change much during training. But on the other hand, we also see that this overparameterization can only explain a part of the picture. In itself, it cannot explain learnability, even of very simple function classes, such as single ReLU neurons. And a very natural question here that, again, a lot of people are working on as we speak, is to try and show learnability, at least for small, simple networks, beyond this regime of random features. You know, maybe based on that, maybe trying to extend the results in various directions. So to kind of sum up, progress is being made, but you know, the original question, if we're honest, is still largely unsolved. So I'll stop here and take your questions. Thanks. Yes, so that's exactly, it falls into the framework I discussed. So NTK looks a little bit different than what I talked about. So I talked about depth to networks. Maybe I'll go back. Yeah, so I talked about like a case where you think of these as fixed and you just play with the UIs. In some cases, you look at this differently so that the network dynamics behave as if you do a linear prediction over some linearization of the network at its random initialization, and that concentrates around some kernel matrix, and you end up with some kernel function. And that's fine because the framework I discussed and the negative results are for any kind of random feature model, in particular any kind of kernel predictor, and in particular for neural tangent kernels. So this is just a very special case. Any other questions? OK, thank you very much.